talk about coequalisers. Coequalisers are a certain kind of co-limit, and of course they're the dual to equalisers. And they're very useful. They appear all over the place. They give us things like quotients and equivalence relations. And they also tell us an awful lot about monadicity. So remember, the question of monadicity is, given an adjunction, is it a monadic adjunction? And you're thinking about whether its category of algebras is the same as the category that you first started with. And basically, the monadicity theorem says something about nice coequalisers being preserved, formed, things are all made up of coequalisers. And it's very much to do with the fact that every group is a quotient of free groups, which is also a coequaliser statement. So let's have a look and see what a coequaliser is. A coequaliser is a colimit of shape the following thing: a pair of parallel arrows. So let's think about what that actually gives us, more specifically. Given a pair F and G, a coequaliser is, well, so here's our pair. Here's our pair. And first of all, we need a cone, a colimit kind of cone, right? And so you might think that I'm going to draw a vertex and then a pair of arrows like that, because remember that a cone says it's a vertex together with a morphism from every object in your diagram to the vertex. But look, remember that there's this commuting condition, and in this diagram, the commuting condition says that this triangle has to equal this blue arrow, and this triangle also has to equal this blue arrow. And because they both have to equal this blue arrow, what that's really telling us, we don't have to draw this one in anymore. It's kind of irrelevant, because we know that it's got to be equal to this composite and this composite. And you know what that means? It means that this diagram, well, that's all we need. So actually what it is, it's a vertex C equipped with a morphism E like that. This is F and this is G, such that both of these composites are the same. We say that this coequalizes these two parallel arrows. So it's a morphism E with this commuting condition, EF equals EG. And now, of course, we need a universal property. We need this to be the best possible way we could ever have done this, okay? So what we need, this is sometimes called a fork. So what we need is, given any other fork, here is another fork, if I can make my orange appear properly. So here's another fork, and I'll call this arrow S. So such that given any morphism B to V with the same commuting condition, with SF equal SG, well, we've got to have a unique factorization. And because this is a colimit, it comes out of the universal one. Remember, the universal one has to be a factor. So you have to compose it with something else to get the non-universal one. So what this says is that we've got there exists a unique H like that. So let's write it out. Given any one of these, there exists a unique morphism H such that H composed with E equals S. Okay, that is the definition of coequalizer. So let's immediately have an example in the category of sets. What do we get? What we've got to do is we've got to produce some function here that makes this F and G equal in the best possible way. Because look, F and G are two functions now in set. They don't necessarily take A and B to the same thing, right? But we've got to have an E such that after you've done E, they've kind of got glued back together again. So what we're going to take, we're going to take everything in B, and then we're going to quotient out by an equivalence relation. So this is generated by sticking together every f of A to every g of A. So we take f of A and make it equivalent to g of A for all A in A. Now note that there will be, the equivalence relation isn't precisely these things, there'll be more than that, because we might have NB, we could, just like with the push-outs, we could have f of A1 equal to f of A2, right? And then f of A1 would have to be equivalent to g of A1, and that would have to be equivalent to g of A2. And because it's an equivalence relation, transitivity is going to tell us that these two have to be equivalent. But that's not of the form f of A is equivalent to g of A. So we really do have to generate here. Now that we've got ourselves going with equivalence relations, there's a more sort of direct way that we can express equivalence relations. Here, we took a coequalizer and showed that we could make it using an equivalence relation. Right? This time I'm going to start with an equivalence relation and show that we can express it as a coequalizer. So what's an equivalence relation? An equivalence relation on the set B is a bunch of pairs of elements in B, right? Telling us when they're equivalent. So given an equivalence relation, which is going to be expressed as a subset R of B cross B. So this is an equivalence relation on B, right? Now B cross B is all the pairs of elements of B, right? They might not necessarily be pairs of equivalent elements. So R is the subset which consists of just those pairs of elements that are equivalent to one another. But it comes equipped with projection map P1 and P2 back down to B, because these are fundamentally just pairs of elements, right? So we can either take the first element in that pair or the second element in that pair. And guess what? That means that we can take a coequalizer. So if we take that projection down to B, and then we take a coequalizer, the thing that we get here is a set of all the equivalence classes. We get the equivalence set of equivalence classes of that. And so what that's telling us is that we've got this ordered pair of things that are equivalent to one another. On the one hand, we send it to the first component, and on the one hand, we send it to the second. And what we really want to do is stick those two together. So what the equivalence class does is it takes all pairs, it takes all elements that are equivalent to one another and kind of sticks them together, right? And so you can see, I hope, that this equivalence relation is only generated by those pairs of things being equivalent, and it's not actually only those pairs of things being equivalent. Because if it was only pairs of things being equivalent, then all these equivalence classes would only have two elements in them. But in fact, they could have lots, because you've got to keep sticking in all the ones that have ended up equivalent. Okay. So next time, we'll have a look at what happens in the case of groups. What we're going to do now is we're going to look at quotient groups as coequalizers. Remember that the coequalizer looks something like this. I hope you're getting slightly used to reading this kind of diagram dynamically now, saying that there's a universal arrow such that given any other one, there's a unique factorization. We saw last time that coequalizers in set could give us equivalence relations. So now let's have a look at some coequalizers in the category of groups. In the category of groups, supposing we have a group G, supposing we've got a group G and a normal subgroup H. Okay, we know that we can take the quotient of G by H, and here we can now express it as a coequalizer. So we have a coequalizer. So we put our normal subgroup here, and we've got two possible maps going into G, right? The first one is just the inclusion of H in G, which is a perfectly good morphism in the category of groups, and the other one is going to be the zero map, which sends everything down to the identity in G. So it sort of squashes everything down, because one way of thinking about taking quotient groups is that you squash your whole normal subgroup down to the identity, and you sort of pull with it anything else that then has to go with it. And what that is it's a coequalizer. G over H. And this is the quotient map here. So let's just see if we can justify that a little bit. We've got to find out if this universal property is true. Okay, so supposing we've got some other group V, together with a group homomorphism making this commute. Okay, so what's that saying? It's saying, so what this commuting condition is saying, we've got to have that this composite equals this composite. Now this composite down here, everything goes to the identity E. Okay? Because once you've got to the identity, you're stuck. You can never get out again. What about this one? This one goes to, it's an element of H gets included into G and gets sent down by theta. Okay? And we're saying that that has to equal this composite, which means it has to be the identity. So that is such that theta of H equals the identity for all H in our normal subgroup. Okay, so given this theta, we need to try and construct ourselves a unique factorization going down here. Now let's have a little bit of notation. So under the quotient, I've run out of space, so I'm just going to rub that out. If we start with an element G in here, this goes to an equivalence class of G, which we can think of as being, it's the cosets. And the equivalence relation that we have here is that G1 is equivalent to G2 if and only if G2, G1 inverse is in our normal subgroup, right? So now let's see if we can cook up a unique group homomorphism going down to V such that this triangle here commutes. Now what's the obvious thing we could try and do? We can take an equivalence class of G, we can take the coset GH, and we can attempt to send it to theta of G. Let's try and send it to theta of G, question mark. Now, if such a thing existed, we can do this thought experiment where we say, if this existed, it would have to be that. Because look, this equivalence class of G here is the image under the quotient map of the element G. And we know that the element G does go to theta of G. So if such a thing existed, then it would have to send the equivalence class of G to theta of G to make it commute. Okay, so that gives us existence. If it exists, it has to be that. So now let's see whether that actually exists. Well, what do we have to check? We have to check that that really is. Well, first of all, we have to check it's well defined, and moreover, that it's a group homomorphism. So what do we have to do to check it's well defined? So we need to know that if G1 is equivalent to G2, then theta of G1 equals theta of G2. But look, if G1 is equivalent to G2, then that's true. So this gives us, this says that G2, G1 inverse is in H, but we know that hitting that with theta gives us the identity. That was our condition on theta in the first place. So I'll just write it up here. So theta of G2, G1 inverse has to be the identity. But look, this is a group homomorphism, so that implies that theta of G2 multiplied by theta of G1 inverse is the identity, which implies that theta of G2 equals theta of G1, which is exactly the thing that we were trying to find out. So it certainly is well defined. So we've shown it's well defined, and it also has to be a group homomorphism because theta is a group homomorphism. And so if you try this formula on it, we'll discover that that it really is a group homomorphism because remember that if you multiply things in the quotient group, you just multiply the representing elements. So the equivalence class of that multiplied by G2 simply is the equivalence class of G1, G2. That's one of the whole points of it being a normal subgroup. So theta, we're trying to do this map down here, right? So we just define this to be the factorization H. So H of G1, G2 is H of G1, G2, which is by definition H of G1, theta of G1, multiplied by theta of G2, right? So that's exactly what it is that we're trying to find, because on the other hand, I haven't done this in a very organized manner, have I? So that's H of G1, G2. On the other hand, we have H of G1 multiplied by H of G2. And we know that that equals theta of G1, theta of G2. So that gives us the fact that that really is a group homomorphism. So this really is a coequalizer.